Okay, so today we are going to introduce what a row reduced echelon matrix is. So row reduced echelon matrix. So to do the row reduced echelon matrix, first let us consider a simple example of a row reduced matrix, and the row reduced matrix was the last example was okay, what it is 0 1 0. Oh, yeah. So 0 1 0 minus 5 over, sorry, what was that? Minus 5 over 3 or
minus 7 over 9.
Minus 7 over 9.
1 0 0
1 0 0
minus 37 over 9.
minus
37 over 9.
37 over 9. Then
0 0 1
0 0 1
11 by 9.
11 over 9. So this was our last day example of row reduced matrix, right? So as you can see here, in the first row, the leading one is in the second column, and in the second row, the leading one is in the first column, and in the third row, the leading one is in the third column, right? So we can arrange it in a fashion that this is going to be 1 0 0 minus 37 over 9 and 0 1 0 minus 7 over 9 and 0 0 1 11 over 9. Can you tell me which operation I need to perform? So do you understand that we need to use the operation, elementary row operation, third elementary row operation to exchange row 1 and row 2 to do that? And as you can see, there is a pattern here, right? So the first row, in the first row, the first non-zero leading one, the leading one is in the first column. Then in the second row, it is in the second column, and in the third row, it is in the third column, right? So in light of this example, we can define what a row reduced echelon matrix is. Okay, so this is the definition. Sorry. The definition is an M cross N matrix R is called a row reduced echelon matrix if A R is row reduced. So from the previous example, in this example we started with a row reduced matrix, right? So the first condition is R has to be a row reduced matrix. The second condition is all rows of R having all entries 0 occur at the bottom of the matrix. And finally, so what this B is implying, I will discuss a little bit later. So let me finish the definition. See if rows 1, 2 are the non-zero rows of R, and if the leading one of row I occurs in column ki, where I equals to 1, 2, dot dot R, then K1 is less than K2 is less than KR. Okay. So this is the definition of row reduced echelon matrix. So as we saw that A is follows from the last example, and I didn't show you what B is, but C also follows from the last example. So if rows 1 to R, 1, 2 dot dot R are the non-zero rows of R, I mean the row reduced matrix R, and if the leading one of the row I occurs in column Ki, then K1 is less than K2 is less than dot dot KR. So this is the column 1, right? And this is column 2, and this is column 3. So as you can see, 1 is less than 2 is less than 3. Okay. So then let us consider another example. 0, 1, minus 3, 0, half, 0, 0, 1, so 0, 1, 2, 0, 0, 0. So now let us compare the definition with this example. So the first condition is R has to be a row reduced matrix. So is this matrix a row reduced matrix?
Yes.
Why is that?
Because
what was the definition of
one in the row 1, the leading one.
Okay.
First entry is T.
Okay.
The leading also the row 2 there is the first entry is 1.
Okay. Then. But for a row reduced matrix, so every non-zero row, the first non-zero element in that row has to be 1. That is the leading one, right? The leading one happening in the column, in which column, the column has to, all other entries of that column has to be 0. So for this, the first row and the first entry of the first row is this, right? And this is a 1. So this is the leading one of that row, and the column is this, right? And every other element in that column is 0. Then in the second row, the first entry is this, and this is also 1. So this is the leading one, right? And
this is the first non-zero,
non-zero,
not the first entry.
Sorry. And in that column, every other element is also 0. So this is a row reduced matrix then, right? Okay. Then all rows of R having all entries 0 occur at the bottom of the matrix. So as you can see, this row is a 0 row, right? There is all the entries of this row is 0. So B is implying that it has to be in the bottom of the matrix, and this is the last row in that matrix, right? And then if rows, so here row 1 and row 2 have leading one, and there is this is column 2 and this is column 4. So the condition given here follows because 2 is less than 4, right? So this matrix is a row reduced echelon matrix. Okay. So what are the other example? Can be a simple example of a row reduced echelon matrix.
So what is the second condition I didn't see?
Okay, so the second condition is all rows of R having all entries 0 occur at the bottom of the matrix. So in this matrix, okay, let me finish. So in this matrix, all entries 0 is occurs in which row? The third row, right? And it is in the bottom of this matrix.
If there is any zero row,
It has to be in the bottom of that matrix. Okay?
but it is not mandatory to have a zero row, right?
No. So if the 0 row exists, then it has to be in the bottom of that matrix. So that's why I asked you what is the simple example of a row reduced echelon matrix. Can you
Okay,
hear
so
me?
let me ask all of you, write down a zero matrix. 3 times 2 zero matrix. A 3 times 2 zero matrix. Is it a row reduced echelon matrix?
No, it is not row reduced.
Huh? Sorry? It's a 3 times
Okay.
2 zero matrix.
So
Is-
what
is-
SAR is 0, 0, 0, 0, 0, 0.
This matrix. Is
This
it a row
matrix.
reduced echelon matrix?
Why?
It is not row reduced
Can you elaborate?
because there is no leading one.
But I mean, what is the definition?
It has to be row reduced.
Okay.
What is the definition,
Definition of
row
row
reduced
reduced
matrix?
matrix. Yes.
The definition says if there is any non-zero row, the first non-zero entry has to be 1. If there is any non-zero, there is no non-zero row.
I mean, there is no
Does it
restriction.
violate the condition of being row reduced?
No.
So it's a row reduced echelon matrix. So these are examples that clarify your mathematical arguments.
Okay.
Is it clear why it's row reduced echelon matrix?
Yes.
Because in that
So
definition.
if you don't understand it to be a row reduced echelon matrix, it means that you did not understand the definition of a row reduced echelon matrix. So the definition tells you that if there is any non-zero row, it does not tell you that there will not be any. A matrix cannot. A matrix has a row reduced echelon or even what is it called? A row reduced matrix always have to have a non-zero row. Does it tell you? It does not tell you, right? That a matrix always has to have a non-zero row. It tells you that if there is a non-zero row, then the first non-zero entry has to be 1. But in this case, there is no non-zero row. So there is no harm with that. And this is a case which is trivially a row-reduced matrix, which is also a row-reduced echelon matrix, right?
Yeah.
Because since there is no non-zero row, so all the zero rows are stacked together at the bottom of the matrix because there is no non-zero row to argue with, right? Now, give an example of a row-reduced matrix that is not a row-reduced echelon matrix. It's a question. An example of a row-reduced matrix that is not a row-reduced echelon matrix.
If we just replace one of the zeros in the bottom row,
Bottom row, okay. With what?
any number.
No. Not any number because.
1. If we replace the bottom row with 1.
Okay, so you are saying something like this. This.
And 0.
Okay.
0, 0.
This.
So this is an example of a row-reduced matrix that is not row-reduced echelon matrix, right?
Yes.
Very good.
Okay.
Are the row-reduced echelon matrix always row-reduced matrix?
Yes. Because
Follows from the definition. Follows from the definition, right? Okay.
Okay, so now let's. So there. So another example of a row-reduced echelon matrix is the identity matrix, right? Identity matrix of M cross N. So just consider.
Write down the matrix.
Yeah, 1 0 0 0 1 0 0 0 1. So I'm considering 3 cross 3 square matrix, which is the identity matrix. So this matrix, is it a row reduced echelon matrix?
Yes.
Why is that?
Because
So, okay.
The position of the leading one of every row is after the leading one of the other row.
Okay. So that means every row, every non-zero row started with the first row contains a leading one, and second row also, then third row. And can you tell me in the definition there is a condition that is not here. Can you tell me which condition is not here? Yeah, so there is no zero row in this matrix, right? Okay. So let me state a theorem. Every M cross N matrix A is row equivalent to a row reduced echelon matrix. So this is the theorem, and Sir already give you a hint of this theorem, right? So the theorem states that every M cross N matrix A is row equivalent to a row reduced echelon matrix. Okay. So in the previous class, we proved that every matrix A is equivalent to a row reduced matrix, right? In our previous lecture, we proved it. So that means we can start the proof. So I'm giving you a sketch of the proof. So from the previous lecture, we know that every M cross N matrix A is row equivalent to a row reduced matrix. Right? We proved this theorem in the last lecture. So can you tell me how can I proceed to this theorem?
If we
Proceed to
do
the
the
proof.
operation number 3, then we can prove that.
Is that clear to you? Okay, so every M cross N matrix A is row equivalent to a row reduced matrix. So that is clear to you, right? So now let me just okay. So considering a matrix of the form 0. Okay, 1, A, B, C, D, E, F, 0, 0, 0. Is this matrix is row equivalent to a row reduced matrix?
Yes, every matrix is real.
So how can I do that? So I have to start with row 1. So what I can do for row 1 is I can divide row 1 by 8, or I can multiply row 1 by 1 over 8, right?
Sir,
Yeah.
what is the definition of row equivalent argument? I think I missed that.
Okay, so a matrix A M cross N is row equivalent to a
I think you should write an M times N matrix A. That's the size of the matrix.
N
Or you write a matrix of size at M cross
N M cross N matrix A is row equivalent to an M cross N matrix B if B can be obtained from a finite sequence of ERO on the matrix A. Okay, so if you can obtain the matrix B applying a finite sequence of elementary row operation on the matrix A, then we say B is row equivalent to the matrix A. Okay. So this matrix I can make it to a row reduced matrix, right? How? I can start with row 1 and I can multiply this row with 1 over A. Then the
Is
first
A is, do you claim that all these entries are not
non-zero, yes. So all these A, B, C, D, E, F, they are non-zero entries. Okay. So and okay, so then this will be 1, right? And I can apply the second elementary row operation to make this entry 0, right? Yeah. So then I can apply the first ERO in this element entry and I can make it to a 1, and again I can apply the second ERO in the first row to make it a 0, right? So that means this will be something like 1 B prime C prime 0 0 0 0 1. Sorry, there is a 0 and there is a F prime. So this is a row reduced matrix, right? So now what I want to do is so this is a row reduced matrix. What needs to be done in this matrix to make it a row reduced echelon matrix? So I can apply ERO, third type of ERO, and bring this row to the bottom of this matrix, and I can make it to a row reduced echelon matrix. So the theorem, it is said that every M cross N matrix A is row equivalent to a row reduced echelon matrix. That means, and in the last class we proved that every M cross N matrix A is row equivalent to a row reduced matrix. And then what I can do, I can apply the type 3 ERO on this matrix to bring all the 0 row to the bottom of that matrix, right? Then for this condition, I can again use ERO of type 3 to satisfy this condition, right? Is it clear, or do you want me to go through the proof again?
Yes. So it is already fulfilling the.
Yeah, for this example, it is fulfilling, but okay, so let me give you an example of another type. So I can consider another matrix like 0, 1, 2, 3, and 1, 0, 4, 6, 0, 0, 0, 0. So is it a row reduced echelon matrix? It is not. Why? Because this is this is column 1 and this is column 2, but in this is not satisfying the third condition, right? If rows 1, 2, dot dot r are the non-zero rows of R, and if the leading one of row I occurs in the column ki, then it has to satisfy that k1 is less than k2 is less than kr. But here as you can see that in this row and in this row, this is the leading one and this is the leading one, right? So is it satisfying the third condition of the definition? No. So what I can do, I can perform a type 3 elementary row operation in this matrix, and I can write it like 1 0 4 6 0 1 2 3 0 0 0 0, right? So this is a row reduced echelon matrix. Okay. Now let us now let us focus on the system of equation Rx equal to 0, where R is a row reduced echelon matrix. Okay. So so in R we know that 1 2, so we actually let's consider 1 2 dot dot R. These rows are the non-zero, so rows of matrix R. Okay. So and let us consider that so and let the leading one in the ith row occurs at the kth column. And also also 1 is less equals I is less equal R. So from this Rx equals to 0, if I now consider this system Rx equal to 0, can you tell me how many non-trivial equations in this system? Non-trivial equations in this system.
R keep m percent size.
Yeah.
R is size.
Yeah, R is m%. So the size of R, okay, the size of R is m cross n. So how many non-trivial equations in this system? R equations, right? So okay, and so and so and the unknown, there are non-trivial equation in this system. Also note the unknown xki will occur appear only in the ith row, right? So ith row, and these unknowns or variables are called leading variable. So let me give you an example. 0, 1, minus 3, 0, half. 0, 0, 0, 1, 2. This is a system that I'm considering. This is the type of system that I'm considering in this equation, right? So here,
So it's better to write that as a 0 column.
The matrix multiplication is.
yeah, sorry.
There should be x5, x1 on this.
Right?
There
Yeah.
should be x1 on this.
Sorry. X4, X5. So this is a system of type this r is equal to 0, right? So the leading one in the first row is in the column 2, right? So if I multiply it and express it with this x2 minus 3x3 plus half x5 equals to 0. This is one equation. Then x4 plus 2x5 is equals to 0. This is another equation, and the last equation is the trivial equation, right? Okay, so this variable x2 is the leading variable. Here this is also a leading variable. So this is the unknown xi will appear only in the ith row. So note that the unknown xki will appear on the ith row. So in the row 1 there is a leading one, right? And in the row 2 there is another leading one. So the unknown x2 appears in row 1 and unknown x4 appears in row 2. But so ki is what? What is ki here? This ki, let me change the color. What is this ki?
Position of the leading one.
In the
I through
kth column, kith column, because I'm considering I to be the number of row and ki is the number of column where the leading one appears, right? Okay, then so in this case ki is what? This is 2. That's why x2 appears in row 1 and here is a leading one. This is K4. That's why X4 appears in
No. K1 is equal to
1. Sorry, 2.
2 and K2 is equal to 4.
Yeah.
Is that clear to everyone? So please write it.
So
This is K.
1 and this is
Please write K1 is equal to 2 and K2 is equal to 4. So that is why you have X sub 2, that is X sub K1 and that is X sub, yeah, and what is that? X sub K2. No, not
sorry,
K4.
K2. K2.
That's right.
Okay. So then these definitions is matching with our system, right? So, and as you can see, there are other variable as well. This, and this. Okay. So these variables are called, actually, just ignore the coefficients. Just consider this. The variable x3 and x5, these variables are called free variables. Okay. So how many free variables. So how many free variables will there be? No, for this system, yeah. This is 2, but for the system, if I consider this, so there are rows that are non-zero. So yeah. Okay. So the number of columns in this matrix are column in matrix R is n, right? Because this is a m cross n matrix. So Rx equal to 0. So what is the size of this vector x here? N. That means x is a n cross 1 column vector, right? Okay. So
I think it's better not to use the word vector here.
Okay,
It is
sure.
not introduced. So let's call it a matrix, n cross 1 matrix. Just write, you don't have to write all of it.
yeah,
Just a matrix.
n cross 1 matrix, right? So now
Trivial is non-zero, right?
what?
Non-trivial
Non-trivial?
is non-zero.
No. Yeah. Right.
So trivial means 0 is equal to 0.
Okay.
So remember that whenever you have a 0 row there, that produces 0 equal to 0.
So if I multiply this
So-
with this is
So
just
0
0.
row is something that produces a trivial equation. Okay?
Okay.
No, why is it so? Why do you have?
Sorry.
I think you were right
No.
before.
Yeah, sorry. It was right. Okay. So that means there is a possibility of n minus r free variable in X. Right? So,
So I recommend that you go back to your example, the one that you gave. Can
Okay.
you identify the free variables in this case?
X3 minus X3
X3, X5. Is there anything else?
so X,
What about X1? That is also a free variable.
free variables. So,
That is important because that disappeared because of the trivial equation. But that does not eliminate the situation that X1 is a free variable. So there are two leading variables, X2 and X4, and there are three variables, X3, X5, and X1. Remember that. Although X1 is not appearing in any of the equations, but that is a free variable.
different.
All three of them are free variables.
No, okay.
So the difference, we don't care about the difference at this moment. We need to classify the variables. That is the focus at this moment. So we have identified X2 and X4 to be leading variables, and the remaining ones are free variables. What are the remaining ones? X3, X5, and X1. This is how you classify the variables.
So, there are two types of variables. One is the leading variable and the other is the free variables. So, that's why there are n minus r free variables in the system, right? Okay. So, now I can write this Rx equal to 0 system explicitly by xk1 plus j equals to 1 to n minus r c1 j uj equals to 0, xk2 plus j equals to 1 to n minus r c2j uj is equals to 0. So what will be xk of so what should I put here? Xk r, right? Because there are leading variables, so that means I have to put a xkr here. Then this is plus j equals to 1 to n minus r c r j uj is equals to 0. This is the system Rx equal to 0, right? Okay. So what are these? C1j, C2j, or this? I mean, in general, C, I, J, what are these now? These coefficients. So, this is not the coefficients of the matrix R, right? But we can read of this coefficient Cij from the matrix R. So, from the example, as you can see that this is a Cij, this is also a Cij, this is also a Cij, right? But the I and j runs from, for Cij, the I runs from 1 to dot dot r, and j runs from 1 to dot dot n minus r. Right?
So can you translate it into the example?
Yeah, so for this example,
I is equal to 3.
So the I is 1, right? For the first row. So what are the C1Js?
0.
So how many J will be there? 3, because there are 3 free variables, right?
so one is C11, right? Then
So let us first label the free variables. Let us call them U1, U2, U3, right? U1 is equal to X1, U2 is equal to X3, and U3 is equal to X5, right? There are 3 free variables. So what will be the coefficient of X1 in the first equation? 0. There is no X1.
Right.
So C11 is 0.
that means this is just 0 times x1, which is u1, right? And what is the coefficient of x3? This is minus 3, but
That
minus
is-
3, but
That is C1.
in terms of c,
C1, 2.
c1,
2.
is it
1, 3.
No, not 1.
no 1,
C1, 2.
c1, 2,
You
because
are reading things using U's, not X.
okay,
You are comparing it with the theorem, right? So C11 is 0, C12 is minus 3, and C13 is 1/2,
right?
right?
For the
First row.
first, then for the second row,
C21 is 0.
okay,
C22 is also 0.
then
C23 is 2.
okay, then
And then all the rest is 0. C31 is 0, C32 is 0.
no, for the second row, it didn't finish.
Yeah, he already told.
No, sorry, there is another x2, x5 is a free variable.
He mentioned already.
Oh,
He mentioned.
okay, so then yeah, so for this example, what we can do is, yeah,
For the second equation, the free variables are the same, right, as the first one? Or
second
Yeah,
equation,
the free once you determine your leading variables, the remaining are free
free
variables.
variables,
It is the same for all the equations.
because we are in a just one system of equations, right? So in one system of equations,
But from equation to equation, the coefficients will vary, possibly.
okay. So let me finish this example with, so we can assign any numbers to the free variables, okay. So this is let's just set x1 equals to an arbitrary number a, x3 is equals to b, and x5 equals to c, okay. Then the solution will be, so I can just erase this, and the solution will be x2 equals to 3x3 minus half x5, and x4 is equals to minus 2 x5. So
I think it should be 3b minus half c.
no, I didn't. I'm just so just. Okay, let's just. So this is the solution of my system given in this equation or in this, right? So what I did here is I write all these leading variable in terms of free variables, and I can assign any number to the free variable. X1 equals to a, x3 equals to b, and x4 equals to x5 equals to c. This can be any arbitrary non-zero element of the field, right? And so the solution
Why
is
not 0?
also 0. Sorry, it can be 0 because we are considering the trivial system. So 0 is also a solution of this system, right? Does that make sense? So I'm considering this system. So this is a homogeneous system of linear equation. That means it has a solution. It has a trivial solution. X equal to 0 is the trivial solution for this system, right? It is always true for any homogeneous system.
But if we choose only one variable as 0 and calculate the other variables, does that solution also become called that trivial solution?
So if no, for x, so just consider this x1, x2, x3, x4, x5. So if I set x1 equal to 0 and rest of our x2, x3, x4, x5,
We calculate this one equation.
no.
So trivial solution is the case when all these 5 variables
Variables have to be 0.
and that equation, that system is trivially satisfied. Left hand side equal to 0,
Right.
right hand side equal to 0. Because you have chosen all the 5 variables to be identically 0.
So if we
So that is called the trivial solution.
So if we here we can apply a function like can you go down?
Yeah.
So if you don't want to include the trivial solution, we can say that A, B, C not all are equal to 0.
No, but
All is 0.
I can assign any value to this free variable, x1, x3, and x5, right? Because the leading variable here, I wrote all these leading variable in terms of the free variables,
Yeah.
and I can just x1, x3, and x5. I can choose any arbitrary entries from the field,
So that is the reason they are called free variables.
free variables. So I can choose.
They are free to take any value. That is why they are called free variables. But in the case when all these 3 variables are 0, then you also get x2 and x4 to be 0, right? Plug in those values, so you get the trivial solution. Everything is 0.
Yeah. So you can choose like a equal to 0 for a equal to 0, but b and c non-zero.
But that is not a trivial solution.
Yeah. Okay.
X2 and X5 are free variables, right?
Yeah.
But X1,
It is also a free variable,
okay.
right?
So that was the point, that x1 may not appear in the reduced system, but that is still a free variable.
Yeah, so that's why I wrote this. X is a m cross 1 matrix, so n minus r free variables in X. Okay. Okay.
Every variable which is not a leading variable is a free variable.
Free variable. So the solution in terms of ABC can be A 3B minus C over 2, comma, B, comma, minus 2C, comma, C. This is the solution of this system, right? Okay, so now we can write a remark from this example and from the previous discussion, that if Rx equal to 0, so let's consider let Rx equal to 0 is a system of homogeneous equation. So, and if the number R of the non-zero rows in R is less than n, then the system Rx equal to 0 has a non-trivial solution, right? So I'm considering the system Rx equal to 0 where the number R of the non-zero rows in R is less than n. So then the system Rx equal to 0 has a non-trivial solution, right? And the solution, you can write this R leading variable in terms of n minus R free variables, right?
I mean, in this case, you at least have one free variable, right?
Because
your R is strictly less than n, so you have at least one free variable. You can have more. As long as you have at least one free variable, that gives you the freedom of choosing non-trivial solution.
sure. So as we discussed, so we can choose x1 to be 0, x3 to be 0, and x5 to be 0, then the solution is trivial, right? But we have the freedom that any of these, x1, x3 or x5, any one of these cannot be is equals to 0, right? So since I'm considering non-zero rows in R which is strictly less than, so for this case, so it is already R is less than n, right? But since I'm considering less than, that means there is at least one free variable in that system, and I can choose any arbitrary element from the field that and it is non-zero. I can choose 0, but I can also choose non-zero element for that free variable, and that's why the system has a non-trivial solution, right? Okay. Now, so there is another theorem. If A is an M cross N matrix and M is less than N, then the homogeneous system of linear equations Ax equals to 0 has a non-trivial solution. So first, let us take a moment and try to understand the theorem. The theorem says if A is an M cross N matrix and M is less than, then the homogeneous system of linear equations Ax equal to 0 has a non-trivial solution. So what this theorem is saying is, so A is a M cross N matrix, right? And I'm considering the system Ax equal to 0, right? So what I can do is, since A is a M cross N matrix, that means A is row equivalent to a row reduced matrix, row reduced echelon matrix, right? So A is a row equivalent to a row reduced echelon matrix. I am considering that row reduced echelon matrix is just R. Okay. So Rx equal to 0. Now I am considering this system. So since A is row equivalent to R, and from a previous theorem, so I proved this theorem in the last lecture. So we know that the system Ax equal to 0, row equivalent to R, the system Ax equal to 0 and Rx equal to 0 will have exactly same solutions. But R is what? R is a row reduced echelon matrix, right? Okay, so that means there are at least R non-zero rows in this matrix R, right? Right? So, yeah. So, there are at least R non-zero rows.
What is smaller?
Number of rows. So I'm considering in R. So R non-zero rows in the row reduced echelon matrix R, right? and I can write the R leading variable for the system Rx equal to 0. For the system Rx equal to 0, I can write all the x, k, r. These are the leading variable, right? So these I can write x, k, r in terms of the n minus r. Sorry, x, k, r can be written in terms of the n minus r free variable. Free variables, right? So that means Rx equal to 0 has a non-trivial solution. And since Ax equal to 0 is equivalent to Rx equal to 0, that means Ax equal to 0 will have exactly the same solution of Rx equal to 0. But R is less equal M, right? Number of rows in the matrix R is less equal M. And from the statement of the theorem, M is less than N. That means this implies that R is less than N, right? So now we can conclude that if A is an M cross N matrix and M is less than N, then the homogeneous system of linear equations Ax equal to 0 has a non-trivial solution. Is that clear? So we started with Ax equal to 0, and I'm considering that since A is row equivalent to some row reduced echelon matrix, and that echelon matrix I'm considering is R, that means Rx equal to 0 will have the same solution of Ax equal to 0. Sorry, Ax equal to 0 will have the same solution of Rx equal to 0, right? But Rx equal to 0, so there are R free variable in Rx equal to 0 system, sorry, leading variable in Rx equal to 0, and there are n minus R free variable in Rx equal to 0. So I can definitely write all those leading variable in terms of the free variable. But in the matrix R, the number of rows in the matrix R, in this matrix R, the number of rows has to be less equal M, right? Because A is row equivalent to R and the number of rows in A is M. That's why R is less equal small r. Yeah. So at least R. So the small r is less equal the number of row of A, that is M. But in the theorem we state that M is less than N. That means R is less than N. That means what Sir saying that there is at least one free variable in that system. So that's why you can write the leading variable in terms of that free variable, and that's why there is a non-trivial solution in this system Rx equal to 0. And since A is row equivalent to R, that means Ax equal to 0 also have that same solution, same non-trivial solution that Rx equal to 0 has, right? Is that clear? Okay. Now let us take another theorem. if A is an n cross n matrix, then A is row equivalent to n cross n cross n identity matrix if and only if the system system of equation Ax equal to 0 has only the trivial solution. Okay. So this theorem states that if A is an n cross n matrix, then A is row equivalent to the n cross n identity matrix if and only if the system of equations Ax equal to 0 has only the trivial solution. So
Okay,
this
I want to make a comment at this stage. Are you all familiar with the statement if and only if? So please write an implications and on both direction in a bracket.
So sir, I was going to so since if and only if this is so when if and only if comes to the statement of a theorem, you have to prove this theorem in both ways. So that means you have to prove this theorem in the forward direction and the backward direction. Okay. So there is this. Okay. So now start the proof of let us consider the forward direction. First, let's identify what is the forward direction. So the forward direction is if A is an n cross n matrix, then A is row equivalent to the identity matrix. So if A is row equivalent to the identity matrix, then if and only if the system of equation Ax equal to 0 has only the trivial solution. Okay, so we're going to start with that Ax equal to 0. That means the matrix A is row equivalent to the identity matrix of size n cross n, right? So let's Ax equal to 0. Okay, so and sorry. Yeah. So let A is row equivalent identity matrix I. Then from a previous theorem we know that Ax equal to 0 will have the exact same solution will same solution of Ix equal to 0, right? But I is an identity matrix. That means it has only the trivial solution, right? So since Ix equal to 0 only have the trivial solution and the system Ax equal to 0 is equivalent to the system Ix equal to 0, then what will be the solution of Ax equal to 0? only the trivial solution, right? So this is the forward direction. So let's consider the backward direction. Sorry. So the backward direction is what? So Ax equal to 0 has only the trivial solution. So let Ax equal to 0 has only the trivial solution. Okay. So now let us consider another matrix R. Let R be an n cross n row reduced echelon matrix that is row equivalent to yes A. Okay. So that means what? So Rx equal to 0, this system will have exactly same solution of x equal to 0. But we started with x equal to 0 has only the trivial solution. Then yeah. Yeah, so only has the trivial solution. So the non-zero rows in R, let R be the non-zero rows in the matrix R. Okay. So
R be the number of nodes.
yeah. So non-zero rows in R. Then from the previous remarks, it follows that R is greater equal n. So the previous remark, yeah, this remark, this is saying that if R is less than the row of that matrix, if it is less than, then the system Rx equal to 0 has non-trivial solution. But for this theorem, I am considering what? Ax equal to 0 has a non-trivial solution, and I am considering R is row equivalent to A. Then since Ax equal to 0 has only non-trivial solution, that means Rx equal to 0 also have that same non-trivial solution. I mean that non-trivial solution, sorry, trivial solution, right? Then from that remark, I conclude that R is greater equal n, right?
We can write that, but here the rows are only n. So
Yeah.
R can be equal to n. Right?
Yeah, R can be equal to n, but also
R can be greater than n. Because
okay. So I'm not still in that situation. So from using that remark, what I can conclude is R is greater equal n. Is that clear to you? Okay, so let me go to this remark again. So from the previous theorem, we know that we can write a non-trivial, the leading variables of a system in terms of the free variables. So, and the system Rx equal to 0, the system Rx equal to 0 has a non-trivial solution only if R is less than the number of non-zero rows in R, in this matrix R, is less than the number of the rows. So R is what? So let's just yeah. So since this is a non-zero row and this is also a non-zero row, and the number of rows in this system is 3, and the number of rows in this system, non-zero rows in this system is right. Okay. Now, so this remark states that Rx equal to 0 has a non-trivial solution if R is less than n, right? R is less than n. Then the system Rx equal to 0 has a non-trivial solution. So since Ax equal to 0 has non-trivial solution, sorry, trivial solution only, that means Rx equal to 0 also have a trivial solution, and using that remark what I can write is R is less equal n, right? Sorry, greater equal n, R is greater equal n, and but R is what? R is the number of non-zero rows in the matrix R, right? But R is row equivalent to the matrix. R is row equivalent to the matrix A. So and the size of A is n cross n. So R has to be less equal n, right? R is less equal n. No. Non-zero rows. Right? Is that clear to you? Because R is row equivalent to A, that means R is the same size of the matrix A, and R has a so R has total of non-zero rows. The number of total non-zero rows in is R, the small r, this, right? So it has to be less than equal to that this row, number of row, right? So this and this condition, these two condition gives us R equals to n. That means the number of non-zero row in R is equals to n, right? So then what this R is? Then R, this matrix is what? There are non-zero row, sorry, there are n non-zero row in the matrix R. So this is a identity matrix, right? Is that clear? R is a identity matrix because non-zero, so just for the comment, let R equals to 3, small r equals to 3. That means this is a 3 cross 3 matrix, right? So I have to start with, so this is a row reduced echelon matrix. So that means I have to start with a 1, then 0, 0. In the second row, this is 0, 1, 0, 0, 0, 1. Is there any other possibilities for this row reduced echelon matrix? Yeah.
From the when we started the proof from backwards.
Okay.
I think we are sure. Yeah, let's keep it. Which will reduce it.
Right? Is that clear to you? So do you have any other questions regarding this proof? Okay, I think I should conclude here. Okay, thank you very much.